Ratio and root test are very similar tests, and they both arise from the geometric series. So let's review the geometric series. What's a geometric series? It's the sum of a times r to the n minus 1 with n from 1 through infinity, so that if you actually write them out, it's like a plus ar times plus ar squared plus da da da. So every time you advance to the next term, r gets multiplied, so r is called the common ratio. And this summation converges if r is between -1 and 1, right? We know the formula converges to a over 1 minus r. If r is between -1 and 2. If it's not true, if r is 1 or -1, or if it's bigger than 1 or less than -1, then this thing diverges. It does not converge to a single value. Now, to understand what ratio tests and root tests are really doing, you want to apply it to this specific geometric series to see what it's saying. So let's calculate the capital R with the ratio test. Ratio test says you take the nth term, so this is our nth term, an. An is a times r n minus 1. In that case, what is a of n plus 1? Well, you only have to replace n by n plus 1, right? So you get a r n plus 1 minus 1, which these cancel and just get ar to the n, right? So with the ratio test, you have the limit of n going to infinity of, it says I have to do an plus 1 over an, so I take a r to the nth power divided by a r to the n minus 1 power, and all of a's cancel, and when you divide by the same exponential form with the same base, then you just have to subtract the exponents, right? So what is this value? Little r, little r n minus n minus 1, which n cancels, and minus of minus is positive 1. So you get little r absolute value. And we see that the ratio test says if this capital R is less than 1, then the series must converge. What is that really saying about the geometric series? It's saying that if absolute value of r is less than 1, this geometric series converges, but that's exactly the same condition as saying that r is between -1 and 1, right? If r is between -1 and 1, then absolute value of r is indeed less than 1. They're the same thing.
Well,
So,
how come before you chose an to equal ar to n minus 1?
I'm just pointing out that we have this series called geometric series, and because this is the thing that you're adding, this is our an.
Oh.
And then if you're asking me why did I put n minus 1 rather than n, the reason is if I put ar n, then the very first term will be a times r, not a. Okay. The root test also does the same thing. If you take the limit n going to infinity of nth root of nth root of absolute value of an, which is absolute value of ar n minus 1, then because nth root is same as 1 over nth power, and absolute value can be applied to individual factors, when you take n to infinity, this is a limit of n going to infinity of absolute value of a to the 1 over nth power. And when you have something outside, that it gets multiplied to the exponent, right? So you get absolute value of r to the n minus 1 divided by n. What's 1 over infinity?
0.
0. So you get absolute value of a to the 0th power. What's the limit of this exponent when as n goes to infinity?
Infinity over infinity.
N minus 1 over n. Just think about it. If you have like a million minus 1 divided by a million, that's similar
Infinity
to...
over infinity.
No, as an actual value, what is it? 1. It's 1, right? See, the leading term of the top is n, so this limit is same as n over n, which is just 1, right? So you have absolute value of r to the first power, so again you get the absolute value of r. So you can kind of think about the ratio test and the root test both trying to pick out exactly what the common ratio is for very large values of n. Now, let me show you this first example so that you can see exactly how the ratio and root test work. Suppose you have n equals to 1 through infinity, and say 1/2 plus 1 over n is taken to the nth power. The question is, does it converge or diverge? Yes.
N minus 1 over n became 1. Would you use L'Hopital's?
You can use L'Hopital's as well. This is infinity over infinity type, so you differentiate n minus 1, which is 1. If you differentiate n, it's 1, so you end up with 1 power. Okay. All right. So this one, let's try to think about what happens to this series when n is really big. If n is really big, 1 over n is like what? Almost 0, right? So for very large values of n, you're really looking at something like 1/2 to the nth power. What kind of series is this?
Geometry.
It's again geometric, right? Because as you increase the value of n, you have more 1/2 getting multiplied. So even if you didn't know the ratio test or root test, and you were just trying to ballpark the answer, and you were trying to look at this and say, I don't know whether this is going to converge or not, but judging from the shape, it looks like that 1 over n is going to be irrelevant when n is very large. So this will behave like this one, so that since I know that when r is 1/2, that's less than 1 and bigger than -1, it should be converging. So I think this converges. That's like your hunch, right? But that hunch is actually exactly what the ratio test and root test does. And even if you look at the proof of the ratio test and root test, which I'm not going to go over, but if you look at their proofs, that's exactly what it does. It uses it tries to compare the given series with the corresponding geometric series with the same value of r. That's the idea, okay? All right, so let me demonstrate both the ratio test and the root test. I'm going to do root test first because that's easier. And for ratio test, it's slightly harder. Now, it's not always the case that you get the same value of r for both ratio and root. There are cases where they differ. And actually, there's a mathematical proof that says root test is better than the ratio test. Oh, I forgot to say this as well. You see, if r is 1 for the geometric series, we know that it diverges, right? Because if you have 1, then you're adding the same thing over and over again, so it diverges. But there are examples where even if the r value is 1, you might still have a converging series. Okay? So that's something I'll have to show you after this. So when r value becomes 1, you have to say it's inconclusive. What do I mean by inconclusive?
not determined in this test.
We don't know if it's going to be converging or diverging. You need to do some other tests, right? It's just like when you get older like me and you have to get blood work done and the doctor has to see if you have certain disease or some problems. So if you take some tests, sometimes the test comes back positive, or sometimes the test comes back negative. But sometimes the test might be inconclusive, like, oh, you didn't have enough water that day, so I can't trust this, right? And in that case, what do? You have to take another test, right? So if you have performed the ratio test or root test and got inconclusive, that means you have to take a different test. You have to use the limit comparison or whatever other test that's available. Those are the things that you have to use if these don't work out. That said, there are cases where the root test can determine whether it's converging or diverging, while ratio test just gives you a value of 1. So that example I might do or might not. But it's always the case that the root test is stronger than the ratio test. That's proven in math. However, those examples are rare, and mostly you choose one over the other because of the form of your series. So, see, if you have something to the nth power and everything to the nth power, then you want to use root test because taking nth root of that will just get rid of this n, and you get the capital R value very easily. Right? On the other hand, I'm going to show you in the second example that if you have factorials, then ratio test makes more sense. There are some exceptions, but usually if you see factorials, ratio test. If you see everything to the nth power, you use the root test. Yes?
Does it have to be a geometric series for you to use these two?
No, this is not a geometric series.
Oh,
So we already know what the result is for geometric series. You don't have to use these tests. I was applying the ratio test and root test to this geometric series because I want to give you some understanding of why these work. It's basically a comparison to a geometric series. That's the idea. Okay. All right. So let's apply the root test. This is limit n going to infinity nth root of this an. And nth root of n, they cancel. See, nth root is the same as 1 over n power, right? So they cancel. And therefore, you get limit of 1/2 plus 1 over n, but this 1 over n goes to 0. So what's the value? 1/2, right? So, therefore, converges.
You said the n value goes to 0?
No, 1 over n goes to 0. 1 over n, because n is sent to infinity, 1 divided by infinity is 0, right? So you just have 1/2. So the summation of 1/2 plus 1 over n to the nth power, and from 1 to infinity, that will converge, okay? So that's an easy application. Now let's do the ratio test. Ratio test is a bit harder because you have to figure out what an plus 1 is. So first, an is this thing that you're adding. Therefore, what is an plus 1? You replace all the n's by n plus 1. So you have 1/2 plus 1 over n plus 1. And n plus 1. And because you have to take the ratios, it's better to make it into single fractions. So let me rewrite this as n goes here, 2 goes here, so it's n plus 2 over 2n to the nth power. And also an plus 1 if n plus 1 goes here and 2 goes here, then you get n plus 1 plus 3. No, n plus 1 plus 2, which is n plus 3. You get 2n plus 2 to the n plus 1. Now let's try to do limit of n going to infinity of an plus 1 over an. I'm supposed to be putting an absolute value there, but these are both positive, so that's why I didn't have the absolute value there. I'm leaving it out. And then you have n plus 3 over 2n plus 2 to the n plus 1 power divided by n plus 2 over 2n to the nth power, limit n going to infinity. And we use the keep change flip, so this is kept. Right, so let me try to rewrite this as n plus 3 over 2n plus 2 times n plus 3 over 2n plus 2 to the nth power. The reason I can do that is because this is first power and 1 plus n is n plus 1. And then with change, the division becomes multiplication, and you flip this upside down. So you get 2n over n plus 2 to the nth power. And you get limit n going to infinity of n plus 3 over 2n plus 2 times, well, this, if I multiply top to top, 2n times n is 2n squared. 3 times 2n will be 6n. This time, 2n times n will be 2n squared. And then if you FOIL 2n plus 2 times n plus 2, then eventually you're going to get 2n squared plus 6n, and then plus 4 to the nth power.
I have a question.
Yes?
Wait, how did you, the ANs, and how did you get them to be a fraction? Again, n plus 1 plus 2?
So I'm trying to use, I'm trying to use the ratio test. To do the ratio test, you have to compute ratio test. To do the ratio test, you have to compute an plus 1 divided by an.
Right.
That's why I took both of them, I divided them.
Oh, that's just when after you divide.
Yeah, so I figured out what an is, I figured out what an plus 1 is.
I know, I'm saying, how did you get to that AN? That AN?
This an?
The top one.
This one?
No, after the second.
This one? Oh, okay. Oh. I multiply n top and bottom, and 2 top and bottom.
So you just did a common ratio?
Yeah, now you have the common denominator, so you have n plus 2 over 2n. And I did the same here as well. All right, so at this point, this calculation becomes really tough because it's the limit of this is 1, whereas n goes to infinity. So this portion has the form of 1 to the infinity power, which is one of the indeterminate forms. To actually get this, you have to use L'Hopital's, but even that is very tough. So what happens is that if you rewrite this as put plus 4 and minus 4, so that this is same thing as the bottom, which gives you 1, then minus 4, 2n squared plus 6n plus 4, and then to the nth power. And then after this, you can use the L'Hopital's. You write this as e to the ln of this entire thing, right? And well, after that, you can do the jump the frog thing and do the fractions and do L'Hopital's. It's a whole really long calculation. And at the end of the day, what happens is that because this is n squared and this is n, so this n squared makes this go to 0 much faster than this n going to infinity. And that means the 1 becomes 1 faster. This thing becomes 1 faster than the infinity trying to make it bigger or smaller or whatever. So at the end of the day, it will become 1. Okay, and that's a really complicated calculation. I don't want to spend time on that. But that's a demonstration that shows that one is better than the other. So sometimes the choice of root test will be better than choosing the ratio test. Sometimes choosing the ratio test will be better than the root test. I'll give you the second example where ratio test is much easier to calculate. Yes?
But since the root test converges, the ratio, it doesn't, that means what if the root test converges, the root ratio doesn't have to converge?
No, if one test says it converges, then the original test converges. Then so I guess the question is, if the root test converges, what do you know about the ratio test? Well, if the root test says it converges, then the ratio test has only two options. Either it would say it's convergent, or it's inconclusive. You can't say diverge because that's going to be a contradiction in math. Math doesn't have a contradiction, right? You can't have two tests saying, one test saying, oh, this patient is very sick, and the other test saying, oh, he has no problem, to send him home. It doesn't work that way. Like in real life, in medical tests, sometimes that might happen, right? But in mathematical tests, if one says converges, the other one either has to say converges or don't know. Okay. But the reason I'm doing both right now is just to show you that both of them work. Okay. And I want to make a point of getting this 1/2 at the end of the day. Oh, so if you're nervous about how you would solve this on an exam, this is it. This is it. Yeah. You write this much and that's it. This part is just a demonstration to show you what ratio test will do. Okay? And I would never try to do the ratio test. This is just a demonstration purpose. Okay? All right, so this eventually will become 1, very hard. And what about this one? What's the limit of n plus 3 over 2n plus 2? 1 over 2, because n and 2n's are dominating. Or you can also use L'Hopital's differentiate n plus 3, which gives you 1. Differentiate 2n plus 2, which gives you 2. So 1 over 2 will be this limit. So 1/2 times 1 gives you 1/2. And because it's 1/2, you get convergence or divergence? Convergence. Okay. So here's what we see. Originally, when we looked at this series, we were looking at it and said, oh, this looks like a geometric series when n is really large. This will behave like 1/2 to the nth power for big values of n. And because we know that 1/2 to the nth power converges, this should converge as well. That was our hunch, right? And that's exactly what the ratio test and the root test give us. They both say that the common ratio is like 1/2. These values are like the common ratio for large values of n. It's not the exact common ratio. It's slightly off because the actual ratio between two terms is 1/2 plus 1/2, 1 over n, not 1/2 itself. Right? But they both are successfully figuring out that it behaves like the 1/2 to the nth power. Is that good?